Next up, we have Abbas Mohammadi. Abbas Mohammadi is a PhD student in civil and environmental engineering at the University of Utah, whose research focuses on applying computer vision, remote sensing, and data-driven methods to infrastructure and transportation challenges. His work combines advanced technologies such as LiDAR, photogrammetry, and machine learning to develop innovative solutions for safer and more efficient infrastructure systems. All right, I'll turn it over to you, Abbas. Thanks so much.
Thank you, Kyla. Thank you for having me. Hi, everyone. I'm excited to share our work with you that on a very practical things, how to measure soil piles the smart way. This was a team effort. You will see the names here. Many hands made this possible. Next slide, please. So here's the problem in plain words. We need to know how much salt we really have when we need that number often. Because salt is what keeps roads safe. If it gets low, we run short in a storm. And if we get high, we tie up money and yard space. Second, the pile is always changing, loads in, loads out, sometimes every hour. So we need a way to update the numbers quickly. And the third is the old ways no longer suffice. Walking the pile with a tape or stick is slow and not safe. Counting buckets is inexact. Climbing or working near loaders at risk. And work often has to stop. So the need is clear, a method that is safe, fast, and accurate that crews can do without shutting the yard down inside the shed or outside, and that gives a number we can trust and record. Next slide, please. On the slide, we would have a quick look at LiDAR. LiDAR sends out tiny laser pulses and times how long they take to bounce back. If we know that time, we know the distance. It gives us a point cloud. It's very accurate, works indoor, outdoors, doesn't care if the pile looks plain or has little texture. But this gear can be expensive and you need a steady setup and a short checklist to have a good scan. Next slide, please. The next tech is the depth camera. This tool takes two pictures at once, a normal color photo and a distance picture. Put them together and you get a quick 3D view. There are a few kinds: stereo, structured light, time of flight. It's small, fast, simple. You can walk around the pile and get a rough model in minutes. No tripod, no drone. But the drawback is the range is short, so big piles are hard. And also bright sun or very dim light can confuse the sensor. Next slide, please. The next method is photogrammetry. The idea is simple. We take many overlapping photos or a continuous video of the pile, walking all the way around and a little higher for the top. The computer then matches the pictures and builds a 3D model. It's safe, fast, and is low cost. Next, please. On this project, we used two kinds of LiDAR. First is a phone-based LiDAR with the Polycam app. It's a scanner that's built into newer iPhones and iPad Pros. We open the app, walk a slow loop around the pile, and the app builds a quick 3D model. It's easy and fast, but the range is short. This is great for quick checks or when we just need a rough number. Second is a tripod scanner, the iSight 8820 you see here. We set it up on a tripod, scan from one spot, and then move once or twice to see around walls and corner. It takes a little more time on site, but the quality is excellent. So the big picture is phone LiDAR is fast and handy, and the tripod LiDAR gives us the best accuracy. Next, please. For the depth camera, we use the Intel Sense D455. It's a small bar-shaped camera with two eyes, plus a color camera. It plugs into a laptop and gives us a color picture and distance picture at the same time. Next, please. We use normal smartphones, but any recent phone with a good camera works for photogrammetry. You will also see a tall pole. This let us get a few high, safe shots over the pile without climbing. The next slide, please. Thank you. Now let's talk about the drone setup we use. This is a DJI Mavic 3. It gives us a clean view of the top of the pile and the area around it. It's fast, safe, and great for big outdoor piles. Uh, it seems to be the most accurate option when we have enough space over the pile. So we chose this one as a ground truth for our analysis. Next slide, please. Also, we use two main software, 3ds Zephyr for developing and creating the 3D point clouds, and the Cloud Compare software for the final volume measurements. Next slide, please. To make sure this works in the real world, we went to 7 UDOT facilities. We picked a mix of sites, some piles inside sheds with one open side or two open sided, and some out in the open that gave us different shapes, size, lighting, like bright sun, shade, and tight corners near walls. Next, please. These images are from the tripod LiDAR at Marie site. The scanner does okay on shape, but it only sees what it can see from each spot. When the pile is tall, part of the backside are hidden. Even with 2 or 3 setups, you can still miss pieces near walls and steep slopes unless you spend more time moving and re-scanning. Also, the gear is not cheap. The unit and software cost a lot, and the setup takes time. Lining up multiple scans is a bit tricky and needs someone with experience to get it right every time. So for our project goal, fast, safe, repeatable checks, this isn't the best fit, and we have to rule out this option. Next, please. These models come from mobile phone LiDAR. Can you please, these two are videos. Can you please play the videos for each one, for the models? Thank you. On the left, the Salt Lake East, you can see it worked great. The pile was moderate in height, and the phone could see most of the surface. The result was complete and smooth. But on the right, in Draper, the pile was too tall. The phone LiDAR has a short range, so parts on the backside were out of view. Phone LiDAR is not expensive, and it's easy to use, but the coverage is limited. So we rule out these two for day-to-day inventory. It's fine for small piles, for quick checks, but not for the routine counts across the different facilities. Next, please. These are the depth camera results at the Marie site. On the left is the depth image. In the middle is the color photo, and on the right, you can see the point cloud we get. You can see the model is thin, spotty, not even a 3D point cloud. Why this happens? Short range, salt surface is light, grainy, and can be shiny. That makes the sensor lose pixels. The lighting is another problem. Sheds have, dark corners and the sensor struggles. The other problem is coverage and occlusions, and also it has a motion sensitivity. Because of these gaps, we can't make a closed surface, so any volume would be a guess. So fixing it also take a lot of manual patching, slow and not repeatable. So this device is also not a good option for day-to-day inventory. Next, please. From now on, you will see the result from photogrammetry method. On the left, the phone-based photogrammetry result, and on the right, drone-based photogrammetry result. Both looks complete. We see the top, sides, the floor near the walls, the surface is smooth, not spotty, and the shape match what we saw on site. Why this works well? We get full coverage, and also the photos grab lots of details. Next, please. Here's just another example of the chip pile outside the shed in Mount Pleasant. Next, please. Is another example of also chip pile in Selena. Phone base on the left and drone base on the right, obviously. Next, please. Here the results in Marie side, but here the real lesson learned. At Marie, our photo model missed the very top of the pie, as you can see at the left image. You can see that a small flat spot where the model didn't close. This can happen to any crew, so let me show and tell you how to prevent it and how to fix it. To prevent it, we have to do a second high pass, use the pole and tilt the camera down at the crest. Also take a few oblique shots from each corner so the top is seen from different angles. Next, please. And to fix it, we can easily use the Cloud Compare software, draw a small outline around the gap at the crest, and use the patch tool to cap the hole so the pile is a closed shape. And with those extra shots or a quick patch, you get a complete reliable volume from the phone-based photogrammetry. Next, please. After developing the model in the 3D software, we exported into Cloud Compare software, which you can see the result of volume measurement on the right. It's a very quick and safe routine we use every time. We just set the floor, trim the model, remove anything if we got any stray items or anything below the floor, and close the gaps and just run the volume, and we record the number in cubic foot or cubic yards. Next, please. We can easily do the same for the drone-based photogrammetry. Next, please. And here's what the numbers look like at the Draper site. That's difference of 11 cubic yards. If you divide 11 by 708, you get about 1.6%. In plain words, the foam method is within 1 to 2% of the drone. So that's a good reliable method for day-to-day inventory. Next, please. At the tool site, we also work with 5C strategy. They have fixed LiDAR sensor on the roof. I think something like what Andy told us before. The system scans the pile on its own and sends the volume to a web portal, no crew time once it's set up. And on the left is our phone photo model. On the right is the drone model, both looks complete. And how the fixed system works is we take one bare floor baseline, then the roof sensor scan on a schedule and compute the change in volume. And if the floor gets regraded or the walls move, they have to do re-baseline. This is great for a busy yard that wants daily or even hourly numbers with almost no on-site work. Next, please. Here are the volume views for the phone-based and drone model photogrammetry. Next, please. And here are the numbers, phone photogrammetry, drone photogrammetry, and 5C fixed LiDAR. The phone result was higher than the drone by about 9%, and the fixed LiDAR matched the drone very closely. Next, please. Here are our results across 7 sites. The phone method stays very close to drone, about 1.5 to 6% off with an average about 3.8. Phone photogrammetry gives trustworthy volume for daily use, fast, safe, and cheap. If yours wants always on tracking, probably adding fixed LiDAR would be the best option. Next, please. Here is a time cost story. The phone photogrammetry time about 5 minutes to take photos, 20 minutes to process. Cost is almost cheap, a camera pole and a software license. The drone is the next, take about 50 minutes to fly, 20 minutes to process. And cost is the drone plus the software license. And it would be the best for using outside when you want super clean top coverage. And the next one is fixed roof-mounted LiDAR. The crew time after setup is basically 0. The system scans on its own and calculates the volume. The processing is automatic. Numbers go to a web portal. and cost is higher upfront, hardware plus a service fee probably. It makes sense at busy sites that need daily or hourly numbers. So the plan is probably simple: use phone photos for routine, very quick checks. Add drone for big outdoor piles, and use fixed LiDAR at a few key sites where you want always on inventory with almost no crew time. Next, please. Yes, to wrap up, photogrammetry, probably the quickest for big busy sites. Fixed LiDAR, and third is we don't use tripod LiDAR or phone LiDAR for routine checks. Tripod is costly, slow, phone LiDAR miss tall pile bags. And the depth camera didn't do well on the big salt piles. And standards SOP for the photogrammetry is like, capture photos with overlap, enclosure, the modeling, do some quality control check, and just run the volume. Train crews once and track the results always. Thank you.